All right, so very quickly, tangent and cotangent, remember, are not just reciprocals of each other. They are cofunctions of each other. And the co means what? Co means complementary. So the functions only differ by 90 degrees or pi halves radians. So here's what we're going to do for tangent. The default period for tangent is what? No, pi. 1 pi, yeah. And we only count by half cycles, not quarter cycles. So I'm going to call this pi right here, and then half of that's pi halves. That's all you need to do is bisect it once because you have your half cycle interval. So we have 0, 1 pi halves, 2 pi halves, I'll call that 3 pi halves. And then at least one negative value, I'll call that negative pi halves. So how many critical values do we need then for 2 cycles of tangent and cotangent? We need 9 for sine and cosine. Yeah, we only need 5 for tangent and cotangent. So there's enough right there. We have 5. But I have enough room. I'm going to go ahead and throw one more down there, negative pi. Now that's actually what I'm going to copy and paste for my next one. I'm going to get rid of that. You don't want to sketch them on the same graph in this case because they're going to kind of interfere with each other. All right, so the only thing you have to remember now, the difference between tangent and cotangent is 2 things. First of all, where tangent starts on the y-axis. Does it start with an inflection value or does it start with a vertical asymptote? Inflection value, bless you. Tangent starts with an inflection value, and because there's only 2 types of critical values, once you have one of them, you have all the others in sequence. They just alternate. So the next critical value is going to be a vertical asymptote. And then you go back to an inflection value, and then a vertical asymptote. And you just alternate that way. Working back to the left, I guess we're on vertical asymptote, and then another inflection value. Now before I connect the dots, I'm going to go ahead and get the critical values for cotangent. Cotangent on the y-axis starts with a vertical asymptote. Yeah. And again, once you have one of them, you have the rest of them, because the next critical value is going to be the opposite, or the other one, sorry, not the opposite. So we have inflection value, and then another vertical asymptote, and another inflection value, and then we just keep that alternating pattern for as many critical values as we have. So we're counting by half cycle intervals. Now before we connect the dots, it's real easy to see here why tangent and cotangent are cofunctions of each other. Because if you pick the graph of tangents up with the critical values and shift it over 90 degrees or pi halves radians, it'll be exactly what we have marked on the cotangent graph and vice versa. Okay, so they're cofunctions of each other. But the other thing that's different between the two is the type of graph they are, whether increasing or decreasing. Tangent is monotonic or strictly what over its domain? Increasing, yeah. So you want to make sure when you sketch the graph that you're using the inflection value for that purpose of changing the curvature. Increasing concave down to the left, increasing concave up like a cup to the right. And each of those little branches should be somewhat symmetrical to each other, but, you know, differences are fine. Cotangent then is a monotonic or strictly decreasing function. So you always want to draw your vertical asymptotes first because they are guidelines. They help you, they give you something to draw the graph towards. So always put those first. So there you go. I only asked for 2 cycles, and I did 2.5 cycles because it's always good to go above and beyond. Okay, just a smidgen. And there you go. So if you have those 2 guys memorized, you can start sketching transformations of both of those pretty easily. I don't think it's worth memorizing TIV or CVI, you know, to help you remember the parent functions. Just remember that tangent of 0 is 0, right? So it passes through the origin. And cotangent of 0 is undefined. Hello, Dominic. Dominic just came in. All right. So any questions on the warm-up? You got those memorized? Sure, good. So let's move on to then example 3. We are now going to sketch several cycles. I know what I wanted to do. One last thing. Just as we wrote equations of sine in terms of cosine and cosine in terms of sine, we can do the same thing here with tangent and cotangent because they're cofunctions of each other. So here's what I want to do before I get to example 3. I want to write the tangent graph, which is f of x. I want to write the equation in terms of the cofunction of tangent, which is cotangent. Okay? I want it to be the exact same graph as tangent, but I want to write it in terms of cotangent. So help me out with that. I'll put my cotangent down. What's one thing for sure that we're going to have to do? If I want to start with a cotangent graph and turn it into the tangent graph, cotangent's a decreasing function, right? Tangent's increasing. So the only way to take a decreasing function and make it into an increasing function, in this case, is to reflect it across the x-axis, right? If you reflect it across the x-axis, it'll change from decreasing to increasing. And so the way we do that is with the negative a value up front. So if the a value of tangent is 1, the a value of cotangent is going to be -1. And that's going to be a common characteristic. Anytime you're writing a graph of tangent or cotangent in terms of the other guy, you're always going to have to change the sign of whatever the amplitude currently is. Always, all right? And then the other thing, of course, that we have to do, which is the same for sine and cosine, is we're going to have some kind of horizontal shift. So all we have to do to write a graph in terms of cotangent is to get over on the graph of tangent to where cotangent normally lives on the y-axis, which is a vertical asymptote, right? Cotangent normally starts with the vertical asymptote on the y-axis. So go to the tangent graph and pick out your favorite vertical asymptote. My favorite's not showing. It's at 5 pi halves. Pi halves, yeah, that's the easy one. Pi halves, so you want to shift it over to the right pi halves? That's going to be x. Well, if you want to shift it to the right, it's x minus pi halves. But would x plus pi halves also work here? Yeah, it would also work. Yeah. And there you go. There's a very nice visual then of the cofunction nature of tangent and cotangent. Now, we said yesterday that cotangent was what? Even, odd, or neither? Odd, right? So let's review that. If cotangent is odd, then what that means is cotangent of a negative input is equal to the opposite of cotangent of a positive input. So, guess what I could do with the negative in front of the cotangent then? If this were like a multiple choice question, and I say which of the following equations is equivalent to tangent, this might be an answer choice right there, but because of the odd nature of cotangent, I could actually use the identity, as we're going to call that, and bring the negative inside. And that would then distribute to both of them, and that would become cotangent of negative x plus pi halves, or pi halves minus x. And that is exactly the same as that by using the cofunction, or actually by using the even odd nature of the cotangent, which is actually an odd function. Okay? Let's do the same thing over here for cotangent. Let's write it in terms of tangent. Very quickly, what, of course, is going to have to be the new value of A? If I want to write that graph above in terms of tangent, it's going to have to be negative because tangent's increasing and I want it to now be decreasing. And then all I have to do is shift over to a point on the graph that tangent normally exhibits on the y-axis. Tangent normally has an inflection value on the y-axis. So go to this graph here and pick out your favorite inflection value. I'll choose pi halves again. Oh, let's do negative pi halves. If I shift over, I can get plus pi halves, and you end up with an equivalent equation of the graph of cotangent. And of course, in this case, because tangent is also what type of function? Even, odd, or neither? Odd. You could bring the negative inside and distribute it, and you get negative x minus pi halves. But that's a little bit uglier because they're both negative now. But it is equivalent. So remember, with the identities, if you have a negative b value and the function's odd, you could bring it out front, which is typically what we're going to do when we're graphing. But it works the other way around. If you have a negative a value out front, you could bring it in and change the sign of the b value. All right, now I think we're ready for example 3. We're going to sketch 2 cycles of each of these, and then we're going to write an equation of it in terms of its cofunction. So step 1 is to identify the parent function, and I'm looking at it and I'm guessing log. Log base 10, is that right? I'm really bad at this. Tangent, very good, tangent, okay. So that's step 1. Next step is to see if it's in standard transformation form. If it is, you're good to start graphing it. If not, you need to put it into standard transformation form. What do we know about this one? Yes or no? Yes, it's good to go. All right, so let's talk about what each of these are going to do. The 2, it's not the amplitude anymore, but it's still going to be a vertical, what? Stretch, bless you, by a factor of 2. So the graph is twice as tall. And the +1, is that inside or outside the angle? Is that a B value or a C value or a D value? It's a D value. Yeah, if it were meant to be inside, it would have to have parentheses. So that's a D value, so that's just going to be up 1. So we don't really have a sinusoidal axis, but what that means in terms of up 1 is all of our inflection values now are going to be up along the line y equals 1 instead of on the x-axis. All right, but other than that, we're not changing the period, we're not shifting it, so I think we can go straight to a graph. There it is. The period is what of this function? Pi. So I'll come out about 2/3 of the way, call it pi. Half of that is pi halves. And that's all we really need. So now I have my half cycle counting interval. 0, 1 pi halves, 2 pi halves. I'll put a 3 pi halves over there and a negative pi halves. Do I have my 5 critical values? At least one of which is negative? I do. So that's it. Okay, so since there's no horizontal shift, tangent then has a what at 0? Vertical asymptote or an inflection value? Inflection value. So I'm going to put an inflection value down at 0, but not at the origin, because remember everything is up 1 unit. So I'll just mark a 1 right there, and I'll put my solid dot. I don't think it's worth drawing a horizontal line through y equals 1, because we're not going to be referencing above and below. As I just go from one critical value to the next, I'm going to put all my inflection values kind of along the same vertical line or horizontal line. So then the next one will be pi halves vertical asymptote, and then pi comma 1 is another inflection value, 3 pi halves vertical asymptote, and then negative pi halves would be a vertical asymptote. I'll throw one more in here, negative pi, and that would be a vertical asymptote. So you just alternate, right? Is that right? Yeah, I did that. I wanted to call pi halves an inflection value and negative pi a vertical asymptote, but that's backwards. Yeah, we have another inflection value. There we go. So you just alternate. I had trouble with that. See if I can get better. Okay, so now we're ready to start connecting dots. And here all you have to do then is tell yourself, is it going to be increasing or decreasing? It's going to be increasing. Now, how are we going to show that it's twice as steep as the original one? Have we ever really showed those on our graphs? No, I'm not going to measure it. So as long as you have it increasing, I'm just going to assume that you know that it's twice as steep as the original graph. You should be able to describe it to me from the equation, vertical stretch by a factor of 2. But in terms of showing it, there's nothing I'm going to measure. So there you go. That's good enough. It's a beautiful graph. And then from there, bless you, you can get the domain, you can get the range, you can tell me the coordinates of an inflection value, you can tell me the equations of a vertical asymptote, all that good stuff. Let's go ahead and write an equivalent equation in terms of cotangent. So for cotangent, what's our new value of A going to be? -2. You're always going to change the sign in the front. And then aside from that, the really only difference is the horizontal shift. You're still going to have the +1. Cotangent normally has a what on the y-axis? Vertical asymptote, right? So now all you have to do is get over to one of those features. Which vertical asymptote do you want to get over to? Let's do 3 pi halves. A little crazy, okay? So if I want to shift to the right to 3 pi halves, it's going to be x minus 3 pi halves. And that's it. It's that easy. Of course, there are other answers. All right, questions on A? Kind of fun? Kind of boring? Kind of in between? You like it? All math is fun. Good. Even the boring stuff. Yeah, because it's still math, right? All right, letter B. Y equals negative cotangent of x minus 1. What's the parent function? Cotangent. The negative in front is going to reflect it across the x-axis, which makes it a what type of function? Increasing or decreasing? Increasing. It's now increasing. The minus 1 does what? Right one? Down one. Good. No value of C here, no value of B other than 1. So we can go ahead and put our marks on there. The period is what? Pi, same as before. So there's 1 pi, there's pi halves, there's 1 pi halves, 2 pi halves, 3 pi halves. 0 is still one of them, negative pi halves, and negative pi. All right. There's no horizontal shift. So cotangent starts with the what on the y-axis? Vertical asymptote. So we'll throw the vertical asymptote on there. We're down 1 now, so I'll mark that as negative 1. Pi halves negative 1 then is the inflection value. And then we alternate, so we're at a vertical asymptote. 3 pi halves negative 1 is another inflection value. And here's where I messed up last time. I'm not going to mess up now. So going to the left, we have a vertical asymptote at 0. So now we have a inflection value at negative pi halves negative 1, and then a vertical asymptote at negative pi. So there it is. It's setting it up. And now all we have to do is connect the dots with a, again, I forgot. What type of function? Increasing? All right, increasing, because it's a cotangent with a flip. All right, so an increasing function. So again, draw it to your inflection values. Increasing concave down, and then increasing concave up. Increasing concave down, increasing concave up. And again, at least 2 cycles with at least 1 negative. Go ahead and, I try to do this, but sometimes I forget. Put arrows on the end of your graphs. And keep them in between the horizontal or the vertical asymptotes. They don't extend out horizontally like x cubed forever and ever. So then the last order of business here is to write an equivalent equation in terms of, can we write one in terms of sine? No. Cofunction, though, we can. So for tangent, what's my new a value for tangent? Positive 1. It's already increasing. So it's just tangent of, and now I need to shift over to a feature of tangent that normally exists on the y-axis, which is an inflection value. Do we have an inflection value anywhere? Sure, we have 3 of them shown. Let's do the easy one and shift over to the right to pi halves. So it's x minus pi halves. So perhaps another boring one, but still, as Dalton said, still fun, which is why time is flying by. It's almost 3rd period already. We have 30 minutes. Questions on B? Questions on A? Questions on C? Well, we should probably do C before I ask for questions. Yeah, how do you do C? Let's do it. This is a little more interesting because notice now we have some horizontal action going on, right? We have a B value of 2 and a C value of pi fourths. So the 2 is going to do what to the graph? Horizontal compression. Good. Horizontal compression by a factor of 2. That's going to change the period. So if typically we see 1 cycle between 0 and pi, and now we're compressing it by a factor of 2, remember that's going to tell you the number of cycles now in pi. So we're going to see 2 cycles. So in general, the period is the old period divided by the number of cycles you're trying to squeeze into that space, which is your absolute value of b. So what's the new period here? Pi halves. Is it in standard transformation form? Yeah, so we're just shifting it right by pi fourths. Now, do we need to make a sacrificial axis? Let's see. If pi halves is the period, we're always counting by what fraction of the period for critical values for tangent and cotangent? A fourth or a half? We only count by a half cycle. So what's a half of pi halves? Pi fourths. Oh, so that's easy. So we're just picking the graph up and moving it over pi fourths, which is where the next critical value would be. so we don't have to make new marks. And I'm not going to have you make new marks for tangent and cotangent like we did for sine and cosine. So we can go straight to the final graph here. So to get our critical values, we go out to pi halves, about 2/3 of the way, and we bisect it one time, and that gives us pi fourths. And now we have our half cycle counting interval. So 0, 1 pi fourths, 2 pi fourths, that'll be 3 pi fourths out there. And then at least 1 to the left, negative pi fourths. And there it is. There's your 5 critical values. That's all you really need. Okay, so now I need to start. Do we need to mark the y-axis up? I don't know if we really addressed that here. For sine and cosine, we always did. There's no vertical shift here, so our inflection values are on the x-axis. But we don't need to label anything like a high and low, because what's the range of all these functions? All real numbers, yeah. So we don't have to mess with the y-axis here. But we do want to put down our critical values, and so here's how we'll do it. Tangent normally starts with a what on the y-axis? Inflection value. We're moving everything over pi fourths, so the inflection value at 0 is now at pi fourths. So that's where you put it, pi fourths comma 0. And again, with tangent and cotangent, all you need is one critical value, and then after that, everything just alternates. It's not like sine and cosine where from an axis you can go either high or low. It's just inflection value, and the next one is vertical asymptote, then inflection value, and then working the other way, vertical asymptote, inflection value, so on and so forth. So there you go, you've set the table. And now you got to do is connect the dots with what type of graph? Increasing or decreasing? Increasing, yeah, because we didn't flip it. So it'll be increasing. And again, make sure that you're showing the curvature change at the inflection values. Exaggerate it, bless you, if you have to, bless you. All right, the equation then in terms of the cofunction. What's the new a value for cotangent of this graph? -1, good. We still have the 2, because that's still, the period is the period, but now we just need to shift over to a cotangent feature. 0, good. We have a vertical asymptote already on the y-axis, so we don't even really need a phase shift. We can cut that shift out, right? We can just call it negative cotangent of 2x. You could do x minus pi halves if you really want, but negative cotangent of 2x works great. Anyone falling asleep? It is boring. I apologize. Like some of the kiddie roller coasters, they're still fun, right, Dalton? But sometimes you fall asleep on the roller coaster because it's like fun but boring, right? We're kind of in that area right here. Fun but still boring. I don't want to put y'all to sleep. All right, so let's do D. D is a little bit more exciting. Maybe this roller coaster has like, maybe not a loop, but maybe a barrel roll. Yeah, I don't know. What's more fun in your mind? I don't know. 2 cotangent of 3x minus pi halves. What's the parent function? Cotangent, good. So this function is going to be increasing or decreasing? Decreasing, good. Is it in standard transformation form? Not quite. Very close, but not quite. I do have to factor the 3 out on the inside, so let's go ahead and do that. I get 2 cotangent, factor out the 3, x minus something. When you factor a 3 out of pi halves, you get a pi what? 6. Because remember, factoring out is dividing out. So pi halves divided by 3 is pi 6. And of course, you mentally redistribute to check your work. I know you do that. The a value is 2, so we're just going to draw it twice as steep as we normally would, right? Wink, wink. But the 3 is important because that's going to be a horizontal compression. And so what's the new period? Pi thirds. Pi divided by b, pi over 3. When do we start with 2 pi? Only for sine and cosine. Tangent and cotangent always start with pi because that's the default period. So pi over b for tangent and cotangent. All right, so if the period is pi thirds, what's the half cycle counting interval? What's a half of the period? Pi 6. So once again, kind of boring. Maybe it's a hint at a barrel roll. Maybe we're just leaning on the roller coaster. We're picking it up and moving it over one critical value. Kind of boring. Okay, so we can go straight to our final graph. Y-axis, x-axis, and we'll throw the points down. The period is pi thirds. So hopefully this should be coming very routine to you. Pi thirds, half of that is pi 6. So we got 1 pi 6, 2 pi 6. The next critical value would be 3 pi 6, which simplifies to pi halves. Don't forget 0 is still one of them, and negative pi 6. We got the horizontal part taken care of. Now we need to put our critical values down. Cotangent normally has a what on the y-axis? Vertical asymptote, which is now shifted to the right pi 6 units. So we have a vertical asymptote at pi 6. Excuse me. No vertical shift, so our inflection values are on the x-axis. And so now we just alternate. And it's really that easy. There's no d value, so we can just put our values, inflection values on the x-axis. And now we just connect the dots with a function that is going up or down? Going down. So again, I always encourage you to draw your vertical asymptotes first, because it gives you something to draw your graphs towards. And there's 2 cycles. You can get the period, you can get the domain, you can get the range. But let's get the equation of the same graph in terms of tangent. What's the new a value for tangent? -2. Tangent of the b value is still 3. We just have a potentially, well, it's going to be a different shift, but we saw in the last one we didn't have to shift it at all. Do we need to shift it at all here? Nope, because we're looking for an inflection value. And again, we already have one at 0. So if you just want to call it -2 tangent of 3x, you don't even need parentheses around it. That's good. Or tangent of 3 parentheses x minus pi thirds. That works too. All right, so hopefully now you have tangent and cotangent down. So we've met sine and cosine, Sahala and Chala. Tangent and cotangent, you don't need to call them TIV and CVI. Just remember tangent starts at the origin with an inflection value. Cotangent has a vertical asymptote. But that means that there's 2 other trig functions out there that are just waiting in the wings. They want to meet you so very badly. Who are they? Secant and cosecant. So let's go ahead and meet the final 2 trig functions, secant and cosecant. We're going to look at their graphs. And I don't care which one y'all want to look at first. You want to look at cosecant first, or you want to look at sex first? I'm sorry, secant. Oh, my bad. Sorry. That's one of the risks you take when you replace theta with x and you're looking at the secant function. It looks like sex. Okay? And now I ask y'all if y'all want to see sex. And y'all get excited. Let's go ahead and stick with it, but it's secant of x, not sex. So to graph secant of x, we're going to do the same thing that we did when we graphed cotangent. From tangent, how are cosine and secant of x related? Reciprocals. Good. So to graph secant of x, we're going to pretend that we're graphing its reciprocal function cosine of x first. Or let's go ahead and actually graph cosine of x. And then once I have the y values of cosine of x, I can just reciprocate those y values to get the y values of secant of x. Okay? Because the reciprocal of cosine is secant of x. And the reciprocal of abstinence is sex. Okay, but that's a different class. I don't know if that'd be health or biology. Maybe both. Okay. Still boring, right? But fun, still. Cosine, we graphed it by the Chala method. So let me get myself a better x and y axis there. There we go. What was the period, Trevor, of Chala? 2 pi. We're back to 2 pi. So there's 2 pi, 1 pi, and we're counting by quarter cycles again. So there's pi halves and 3 pi halves. and 0. And I'm going to go ahead and sketch a few more than just one on the left because I want to be able to see some symmetry going on here. And then cosine did have an amplitude of 1, so we went up to 1 and down to -1. So I'm going to draw those about halfway on my y-axis. Give myself room for more points. All right, so Chala. Chala was high axis, low axis, high. So we'll put a mark up here, high, then axis, then low, then axis, then high. And then working back the other way, we get this. So cosine was an even function. It had y-axis symmetry. Now, if you want to sketch cosine, feel free. I'm going to go with a light color, something a little darker than white because it won't show up, but yellow, okay? There we go. You can kind of see that. There's the cosine graph in yellow. The reason I did a light color is because I want to sketch the graph of secant, but I want it to stand out a little bit more prominently. Let's use red. I'll use red. So just like before now, what I want to do is take the y values in yellow at the same values of x and plot the reciprocals of those yellow y values. So let's do what we did first with getting cotangent from tangent. Let's look at the x-intercepts. What's the y value on the x-axis? The y value on the x-axis is 0. Good. So what is the reciprocal of 0? Infinity. Some type of infinity, plus or minus. So what graphical feature will manifest on the graph that will force the y values to infinity? A vertical asymptote. Very good. So every x-axis or sinusoidal axis value, as it turns out with the transformation, becomes a vertical asymptote. So we'll draw those in there. Notice this one has vertical asymptotes at pi halves, 3 pi halves, 5 pi halves, so on and so forth, odd pi halves. Which other trig function had vertical asymptotes at odd pi halves? Tangent. So looks like tangent and secant have the same domain. Yeah? Why is that? Well, let's see. Just kind of going off on a mathematical aside here. Secant is r over x, and tangent's definition was y over what? X. So it makes perfect sense. Those are the only two trig functions that have x in their definition in the denominator. X can't be 0 because that'll make it undefined. Now, where's x0 on the unit circle? On the y-axis, which is at pi halves, 3 pi halves, 5 pi halves, so on and so forth. So it makes sense that they have the same domain. Now, to get the rest of our points, let's do the other thing that we did with tangent. The high point of 1, I'm going to graph the reciprocal of that now. What's the reciprocal of 1? 1, right? So the high points are the same point on both graphs. Secant of 0 is 1, cosine of 0 is 1. So the high points stay high. 1 stay 1. What about the low points at -1? What's the reciprocal of -1? -1. So same thing. Cosine of pi is -1. Secant of pi is -1. So the low points stay low. Now, for the other points in between, we have to kind of just look and see what's going on. Let's take right here at pi thirds, just to the left of pi halves. What would cosine of pi thirds be? Cosine of pi thirds. Could have been on like the very first unit circle quiz, and you would have loved that question. Cosine of pi thirds. Nope. 1/2. Yeah. Cosine of pi thirds is a half. So right there at a half, I'm going to graph the reciprocal of a half. What's the reciprocal of a half? 2. 2's up here, right? Now closer to pi halves, I don't know what the angle is, but the y value could be like 1/10, 1 over 10. What's the reciprocal of 1 over 10? 10. That's even higher. And even closer to pi, to the y-axis, closer to pi halves, the y value could be like 1/100. Very small. What's the reciprocal of 1/100? 100. Even higher. And then even closer, the y value could be like 0.000234. What's the reciprocal of 0.000234? 1 over 0.00234, which is a huge number. The reciprocal of a very small number is a very big number. Yeah. So here's how you're going to sketch the graph from the high points. You're going to take your high point at 0, 1, and then you're going to draw it going up and to the right, and then up and to the left. So essentially, the high points stay high, and then you turn upward the graph, turn up the graph towards the vertical asymptotes. And by the same argument down here, you're going to take the low points, keep them the same, and then turn the values downward towards the vertical asymptotes. And you keep them kind of nestled in between the vertical asymptotes, not going outside. And there's the graph of secant. You don't need to remember anything else, because to sketch secant, all you have to do is sketch cosine and then modify the y values. So there's really nothing new to learn. All right, let's talk about then some of the important features of secant. What's the domain of secant? We already talked about it. It's going to be the same domain as tangent. It's going to be all the x values such that x is not equal to where the vertical asymptotes are. And they occur at regular intervals. So remember to do that, we'll pick our non-negative vertical asymptote, which is pi halves, and we'll say plus multiples of how far apart they are from each other. How far apart are the vertical asymptotes? From pi halves to 3 pi halves is pi, right? So we'll say plus pi n, where of course n is an integer again. That's the exact same domain as tangent. And we don't have to say plus or minus pi n, because remember n is an integer. So when n is negative 1, we're subtracting pi. When n is negative 2, we're subtracting 2 pi, so on and so forth. So same domain as tangent. What's the range? It's all real numbers except the ones that don't work. And which ones don't work? We're looking at the red graph now, not the nearly invisible yellow graph. We don't get any values between negative 1 and 1, do we? We get everything outside negative 1 and 1, which makes sense. If sine is between negative 1 and 1, its reciprocal is going to be everything outside. So to do that in interval notation, it's going to be negative infinity up to negative 1. Do I put a beefy bracket or a wimpy parenthesis around that dude? Bracket. They share the high points and the low points. Union, kind of same idea, bracket 1, comma infinity. That's the range. Everything outside the high and low. All right, next thing I guess we need to look at is, well, let's do end behavior, get that out of the way. What is the limit as x goes to infinity? Does it exist? No. None of the trig functions are going to have end behavior. So symmetry is the next big one. Any symmetry going on here? Even, odd, or neither? Y-axis or origin? Yeah, you fold the graph here, matches up. Fold the graph here, matches up. So it appears to have y-axis symmetry, and it does, which is not very surprising because its reciprocal function cosine, from which we derived this graph, also had y-axis symmetry. And of course, any function that has y-axis symmetry we call what? Not odd, but even. Even. Yeah. And so remember what the algebraic consequence of that is. Just like cosine, that means then that secant of a negative input is the same as what? Do we pull the negative up front, or do we just forget about it? Forget about it. It's gone. It's the same as secant of positive x. Negative inputs, positive inputs have the same output, exactly the same, because of the y-axis symmetry. And then the last thing we need to talk about here is the period p. What is the smallest distance in radians for which this graph repeats itself? I want to be able to make a stamp, so I stand on the assembly line and just go stamp, stamp, stamp. 2 pi. Very good. I could get by with making just one stamp if I was on a budget, because I just make one of these parabola-looking things, but then every half cycle I'd have to turn my stamp over. Stamp, 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 stamp. And that's just too much work for me. I'd quit. I wouldn't want to do that. But I could sit there all day and stamp a 2 pi. It takes 1 up and 1 down to complete a cycle. 1 up and 1 down completes the cycle. And then The cycle repeats itself. So the period is, in fact, 2 pi, which is not surprising again because the reciprocal function cosine also had a period of 2 pi. All right, is there anything else you'd like to say about secant of x? Bless you. So has that got you thinking about it? Is there anything else y'all want to say about sex? Good. Good. Is sex the same as gender? Oh, I don't know. Let's not go there. Math is less subjective to argument, right? It's right or it's wrong. Oh, thank you. Keeping us on track. Equations of the vertical asymptotes. Yeah. Vertical asymptotes at x equals, not x not equals, but it's really the same as the values that we had over there. Pi halves plus pi n, where n is an integer. Thank you, thank you, thank you. Inflection values, do we have any? Inflection values, do we have any? No, we don't. Does the curvature change ever, though? The curvature changes. If you look at the branches, you have a frown, which is concave down, then a smile, concave up. Frown, smile. So anytime you go from a frown to a smile, it changes curvature. But we still don't have inflection values because that happens at a vertical asymptote where the graph is not defined. So kind of interesting. All right. Any other comments or questions about this? All right. Speaking of race, I heard that Carl Everett retired from NASCAR. He races no more. I didn't know that. I knew Tony Stewart retired. I didn't know that Carl Everett did. Yeah. Race. Cars. Boom, boom. Sweet. Now, let's go ahead and meet cosecant. We're going to sketch cosecant a little bit faster, but we're going to do it the same way we did for secant. We're just going to pretend that we're sketching what first, do you think? Sine. Good. Let's pretend like we're sketching sine. Sine was Sahala. So there's my x and y axis. I'll come out 2 pi. Half of that is pi. Half of that is pi halves. And then I got 3 pi halves. I got 0, negative pi halves, negative pi. I'll do a few more again to the left than necessary so we can kind of eyeball symmetry. And then I go up to 1 and down to negative 1. So I'm still pretending now that it's sine. Sine is Sahala. So it's axis, high, axis, low, axis. And then working backwards, low, axis, high. Now here's where I'm going to quit pretending. I'm going to quit pretending that it's sine. I'm not going to actually connect the dots. We don't need to connect the dots. Because now we know what to do with the dots. All we have to do to graph cosecant is reuse the critical values of sine. The axis points, whether they're on the x-axis or the new sinusoidal axis, they become what? Vertical asymptotes. The axis points become vertical asymptotes. And then from there, it's easy. The highs stay high, and then you turn them up. And like some of the guys asking girls to prom, the lows stay low, and they get turned down. Oh. Oh. You don't get turned down if you do it right and you ask the right person. Okay, anyway. Highs stay high, they turn upward. The lows stay low, and they turn downwards. And there's the graph of cosecant. Pretty easy to sketch. All right, important information. What's the domain of cosecant? The set of all x such that x ain't equal to 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. How about pi n, where n, of course, is an integer? Hey, that's the same domain as which other parent function? Cotangent, good. Has the exact same domain as cotangent, which makes sense. Cotangent is x over y. Cosecant is r over y. So the only two that have y in the denominator, so y can't be 0, bless you. Y is 0 on the x-axis at 0, pi, 2 pi. Okay? What's the range? Negative infinity to negative 1, union, 1 to infinity. Same as it was for secant. Any symmetry going on here? Even, odd, or neither? Y-axis origin? Yeah, it actually has origin symmetry. Origin symmetric, which means that it is also an odd function. And the consequence of that is, of course, that cosecant then of negative x is equal to negative cosecant of positive x. So every trig function has some type of symmetry. The only two even functions then are cosine and its reciprocal secant. The other four are odd. And the last important thing here is the period. What's the period? We need one branch up and one branch down for a full cycle. 2 pi. There you go. So now every function, of course, that's periodic has a period. The only two then that don't have periods of 2 pi are tangent and cotangent. The other four have periods of 2 pi. All right, so you don't have to memorize secant and cosecant. They come for free if you know the graph of sine and cosine. It's like if you call in the next 15 minutes on that commercial, regardless of when you watch the commercial, if it's in the morning or in the night, they always say if you call in the next 15 minutes, you get whatever, free. Same thing here. If you order Sahala and Chala, you get cosecant and secant absolutely free, as long as you call in the next 15 minutes. We made one commercial. We show it all throughout the day, and in that commercial, we put the 15-minute thing at the end. But it does create a false sense of urgency. Oh, crap, I'm not even near a phone. Oh, but I want to take advantage of this one-time deal. Okay, you got cosecant and secant for free. Chuck Berry died. Yeah. Yeah, Chuck Berry died. Legend of rock and roll. Yeah, he died over the weekend. Yeah, he's a legend. Have a great day.